So if you want to pull up 2 tabs to do this, that's fine. This is kind of the questions that we're going to be answering, okay? And then we'll kind of look at this and figure out how to answer these type of questions, right? And then the second thing is this one, and I don't think we're going to finish in the amount of time we're going to start with, but I really want to get to this. So I'm probably going to hop around with this. So some of this you could just read in the books, but this right here is, I actually might start with this, just number 8, okay? Because this thing, it'll help to see how I'm going to do this. So these I'm going to pull the slides off. In fact, the most important slide is this slide when starting this whole chapter right here, okay? So this is something that happens that you probably don't realize, okay? This is something called disassociation. So what happens is if you grab, this is sodium chloride, and you put little salt crystals in water, what happens? Why does it disappear? It goes through something called dissociation. So an ionic crystal, right? These are like little, I guess for lack of better words, magnets. You know, chlorine's negatively charged and sodium's positively charged, and they stick together. Well, what happens when you stick this stuff in water is that something strange occurs, okay? Water itself is a polar molecule, and we'll go more into that as the chapter occurs. But what happens is water comes in and it basically liberates these ions away from each other. So this right here is the chlorine ion right here. So I'm going to put Cl here. Whoa, let's undo that, right? So I went black so I can see it. So this is chlorine, right? It's negatively charged. And here's a water molecule. And the water consists of oxygen and 2 hydrogens. And you guys all know this. But there's a net negative charge on the oxygen and a net positive charge on the hydrogens. So you can see how the hydrogens are now sort of circumnavigating this little chlorine ion. And when it does that, it's able to pull it off of the actual crystal, right? This is why things dissolve in water. Water is a universal solvent. In chemistry, if we were able to do wet labs, which every time I go to try to do this, something bad happens, and they say, whatever you do, don't let kids do anything because it's a pandemic, right? That you can actually put stuff together and you can measure this change that occurs, okay? So if we look at the sodium end of this, of course, this is sodium and it's positively charged, that the negatively charged oxygens will surround it. And in doing so, it's able to break it free from the crystal. And that is sort of the concept of disassociation. Certain things this works on and certain things this doesn't work on. So this chapter is dedicated to what falls apart in water and what doesn't fall apart in water, right? And there's actually a table that I will get to that I made for understanding this thing. And I'll show you the table ahead of time. We're not there yet, but it is something that we're going to have to, it is something that we're going to have to eventually sort of know is the soluble and insoluble chart. And people kind of like, if you ever heard anybody complain about AP honors chemistry, it's this thing, because it's really, as simple as that chart is, it's a little challenging. And who you hang out with determines who you basically, whether or not you fall apart in water, okay? So to start off with, we got to kind of explain what's happening. What is going on? What's this magic that's occurring? And then we can start looking at the, how would you say, the details, because the devil's in the details, but we're kind of not there yet. I made this little table based on the stuff I've seen in 3 different things, and this is the simplest way to kind of put it together, right? And these were true wet labs that we did. In fact, this is the first wet lab that we did. Unfortunately, we really don't get to do many wet labs until you get to the section, because chemistry's, you got to understand a concept called molarity and all this other stuff. And we don't get to do it till you're into chapter 4. So it's sort of funny because once we get to do this, we can't do this. And this is the fun part of chemistry. You get to measure and see your results. So I know they have something on the Pivot Interactives, and you guys just sort of kind of did one of those simulated labs. They're just not as good, I'll be honest with you, right? But we're going to go through the first thing here. And like I said, you could either do a double pane, you could open a tab and open another tab, and you can look at what's going on. But it kind of follows what's going on in these slides. And if you want, you can ask me a question. I'll stop, and then we can deal with this as we go. So this is reactions in aqueous solutions. And aqueous means in water, obviously, right? So let's define a couple pieces of information. This is straight off that sheet. A solution is anything that's homogeneous, mixture between two or more pure substances. Now,
should we take notes on this?
I would.
Okay.
I would definitely take notes. Because it's actually going to be it's the reading guide. So I'm doing the reading guide with you, reading guide section 1, right? So a solution is anything that has two homogeneous pure substances mixed together. And the word homogeneous means that you cannot tell them apart. It looks clear. It looks all the same, okay? So this is like a really wackadoodle kind of definition, but a solvent is the one that's in the greatest amount, and the solute is the other part, right? So if you think about it, it's kind of an easy way to think of it. Oh, wow, why does it do that? I don't know. So here's solvent is greater than the solute. That's a nice way of kind of looking at it. It's kind of simple, right? So if you have, let's say, 1 kilogram of solvent, and let's say you have 100 grams of the solutes, that's pretty much what you're going to have. So it's kind of a weird way of looking at it, but it is the way it's looked at. So let's do this. And moving on. So this disassociation, I just already gave you a soundbite on that. Something dissolves in water, right? The solvent pulls the individual ions from the crystal and solvates them. It's like solvation, right? It's called disassociation. And I've already kind of explained this. You can see what's going on in that picture. So an electrolyte is a substance that makes ions when it goes into water. And electrolytes, it's sort of important to know, is anytime you have, and let's grab like sodium chloride, NaCl. And now this is a solid, but if I add water to it, let's say you put this in water, it just ends up being Na plus Cl minus. And now we use a designation called aqueous, where this would be a liquid. These are aqueous. This means they're ions floating around in solution. And one time somebody did a project, and it was like trying to find out, looking at the power drinks like Gatorade and this, Powerade or whatever, there's all these different things you can have. Which one has the highest amount of electrolytes? And what was funny is that you have an electrolyte tester. It just basically sends electricity through a little electrode, and they try to measure it, right? This is back when we used to do science projects. And you say, why don't we do those anymore? Well, first of all, you guys kind of hate them. Then the second thing was, in reality, we switched the schedule around and changed the calendars and changed the times of interaction. It became very problematic. I think we have more contact time several years ago, like 10 years ago. So if I had more hours to do stuff, you can dedicate hours to troubleshooting and fixing projects. But since we don't have that, it's just kind of like it became something that was extra, so it kind of got moved away. But one thing that was interesting was that of all the things from Gatorade, Powerade, all that stuff, the one that had the highest amount of electrolytes was hot chocolate. Who'd have thunk it, right? And so the funny thing about it was like, so if you're out there playing, you're playing soccer in the fall, and you're like, God, I really want something to replenish my electrolytes, it would be hot chocolate, but who would have thunk it, right? And part of it's because you have milk in there, and milk with all its proteins and all those little bits in there is going to have quite an influence on your electrolytes, right? So we right along. So an electrolyte is a substance that disassociates into ions, and it can conduct electricity, right? Electrodes in it, right? So this can conduct electricity. Non-electrolyte does not make ions. So something like this, you might remember it from physics last year. If we never got to play with that thing because we left early. before we start playing. But you can get pure deionized water. Yeah, we didn't get to do this. This is so much fun. So if you have H2O, and I have this thing, it's a hand crank generator called a Megger, MEGGER. It's for actually determining ground loops and house current. And this is sort of what it looks like. It's got literally a hand crank on the end of it right here. And if you crank this thing, and if this is pure water, so it's distilled, right, H2O, this will not conduct electricity because there's no electrolytes in it. There's nothing to actually transmit the current. But if you turn around and you put salt water in here, maybe we did do this experiment. I can't. Maybe we did it. I don't know. Anyways, if you put water and then you add a whole bunch of salt into it, like this, and ran this experiment again, this will definitely, you know, if we had a circuit kind of thing set up, this will definitely light a light bulb. I guess it's supposed to be a light bulb. Really badly done. I'm sorry. And if we went back to the generator, this will work because this forms ions, and ions is what transports the electricity through a solution. Okay? Just as a matter of reasoning, the water that's coming out of your faucet has ions in it. So don't think, oh, wow, I'm in a bathtub. It's no, there's tons of salt in there from your skin or from other things that are going to conduct electricity. So yeah, you have to have pure distilled water. That means there's no ions in it for this to actually occur, right? Let's move on to the next guy here. So this is a pretty simple table right here. It almost seems like I don't know why they actually put this in the table. Strong electrolytes are anything that's ionic and certain molecular compounds. And they say the strong acids. Now I'm going to define a strong acid, right? They give you a little table on it, right? Acids are, and you guys remember this from naming, when you put them in water, here's hydrochloric acid, right? It forms H plus aqueous plus Cl minus aqueous in solution. This guy and this guy is going to help conduct that electric current, right? You have to have strong acids for these to work. If you have something that has a weak acid, and we'll look at this stuff, and this gets really talked about, weak acids and weak bases. These are talked more, this is more AP chemistry, and you're trying to measure these things. So we're not really going to go into a whole lot, but one of the more common ones that you could think of is acetic acid, C2H3O2, right? This is acetic acid. That is a weak acid. And what a weak acid is, and we'll look at a picture of it. If you take this guy, HC2H3O2, and I put it into water, so I'm going to add it to H2O, it doesn't totally break down. So you get a double arrow. It goes into something called equilibrium. So you'll get some like this, right? C2H3O2 negative. This would be aqueous, and this is aqueous. And you get some this way. In fact, it's like, I think it's less than 5%. So you got to say like 5% is going to be this, but 95% is like this. So that's why you call it a weak acid. It doesn't fall apart completely. Strong acid, and I think everyone saw me melt a penny at one point in time. That's nitric acid, HNO3. He's a tough one. H2SO4, that first hydrogen that comes off, because it falls off the first one first, HSO4, right? And that's going to be positive charge. I'm sorry. This will be negative charge, and then H plus. That first one comes off easy. The second one takes a little more effort, I'd say, right? So we're going to get into all these guys and try to explain these things. I mean, there's 7 of them. It's not too hard, right? Let's take a look at this next thing. So you could have non-electric electrolytes. A good one is obviously H2O. He's a non-electrolyte. Another one's ethanol. C2H3O2. No, C3H3OH. That's ethanol. They don't really conduct electricity because they're a covalent molecule. And we're saying covalent means it doesn't break apart into its little pieces. Right? That's kind of what we have going on with these guys. We'll see more of that coming up. So molecular compounds tend to be non-electrolytes except for acids and bases. Now, what's a molecular compound and what is an ionic compound? So just to kind of review that, because some people are going to forget that. Ionic, it is a metal plus a non-metal. Molecular is non-metal plus a non-metal. Okay? That's how, whoa, wait a minute here. Hey, you see me doing something here? Those dogs. Anybody want some dogs? Are you serious? I'm going to put you outside in 5 seconds. Let's clear that up. So here's a little light bulb thing. How we would do that. Maybe we can try to play with this next week. We'll put something together of a similar fashion. Right? Give us a try. Pure water does not conduct electricity, so it's not even going to light up. But if you add like sucrose, which is sugar, right, normal table sugar, it's not electrolytic. It will not conduct electricity. However, sodium chloride is going to light up. So it seems so simple and qualitative, but my God, it does tell us the whole story. It kind of works, right? So a strong electrolyte dissociates completely when dissolved in water, and a weak electrolyte only dissociates partially when dissolved in water. So that's the key to this thing. Certain things are not going to come apart. And that has to do with the bonding as well as the attractiveness they have of the two particles or more to each other. So that's kind of interesting, right? Let's do this. So here's the strong acids, and here is your strong bases. Now, before I misguide you inappropriately, I'm going to put this back up here. I'm going to see if that is on that list. I think it is for 401. It says, oh my God, so we're almost all the way done with these things. Look, I've explained this thing except for no one's yelling, hey, what is C-note formation? No, nobody out there want to know that? So I can save you some time looking it up. But we're all down to strong acids, weak electrolytes, chemical equilibrium, acetic acid in solution. I just showed you how's it designated. It's a double arrow. And then these things, we're going to take a look at these next, right? So looking at this, here is your strong acids and strong bases. This must be in 402, if I'm not mistaken. Oh, maybe not. I would write them down anyways. Why are they, you need to know them. So here, write these down. Hydrochloric acid, hydrobromic acid, hydroiodic acid, chloric acid, perchloric acid, nitric acid, and sulfuric acid. And then the strong bases are 1A metal bases and 2A metal hydroxides. These always come up, so you might as well have them all written down. And then I'm going to flip back and we're going to look at some of the those problems. We'll do that together. So let's take a look at these problems. Well, not these problems, 401 problems. Boom. So 415, specify what ions are present in solution when dissolving each of the following substances in water. All righty. This should be easy. So I'm going to do the first one with you, right? It's going to be zinc. That's A. So if I dissolve that, I should get one zinc ion that has a +2 charge and 2 chlorine ions with a negative charge. And more of the same for the rest of these things. You say, I did that? That's not bad, right? Let's do 416, and you guys figure out the rest. What ions are present upon dissolving the following? It's the same thing, right? So this is A for this one, right? Would be Mg 2 plus 2I minus. I'm writing it like this because we're going to use it like this later on. Okay? You don't want to say, you don't do it like this. I'm going to do the international no symbol through it, right? You don't do this. All right, let's do this. Let me grab this thing. You don't want to do it like that. because this says they're still attached together. They're not attached together. In fact, if we really think about it, it would really look like this: Mg plus 2 plus I minus plus I minus. That's why we say it's 2I, okay? So that's kind of the way you want to look at that. You want to say they are not stuck together anymore. They'd be anything but stuck together because they would repel each other. They're both negative, right? So let's go ahead and clean this up, get rid of this stuff.
Dr. Dirk, how did you do that? Like, what was the thought process behind that?
The concept is if you take this, let's say if I take MgI2, and when I put it in water, and that's ionic, right? That's a strong ion. And so when I put that in water, you got to think they are going to basically split right in half. So the positive one, and think about that picture what I had with sodium chloride to getting pulled apart. The magnesium will be here, it'd be +2, and you'd have a negative ion over here. The water molecules will surround it. And like I said, hydrogens will be positively charged. And it's going to surround it like this. You get the point. And the same thing's going to happen with this guy. But this guy, because he's positively charged, remember I said the water molecule has a negative end and a positive end. It's a polar molecule. So this is going to have a net negative charge, and this will have a positive charge. So the oxygens are going to stick to this guy. So he's going to go like this. And once they get surrounded, they are no longer together. It's going to disrupt that ionic bond. So that's why I'm trying to draw a picture like this, but to make it easy, I just use this part. And if I put AQ next to it, it essentially means I'm surrounded by water. Same thing with this one. So I have two of these surrounded by water. Does that make sense? A little more sense, I hope.
Yeah.
Okay, cool. Now I gotta clean up my beautiful, ugly drawing. Let's All right, let's do this. All right. Let's take a look at this next one. Ooh. All right. Formic acid, HCOOH, is a weak electrolyte. You know what formic acid is? You ever been bit by a fire ant? It hurts. Like out in Georgia, they got fire ants. It sucks, all right? And these things have formic acid in it, and it burns, right? It's a weak electrolyte. What solute particles are present in aqueous solution of this compound? What's the chemical equation for the ionization of HCOOH? Now, we talk about an acid. That's why they put the H in front, right? We said that designates an acid. This is going to break off. So in the end, you're going to have a double arrow situation that looks like this. I mean, some of it's going to be like this, and some of it will be how? It'll be H plus aqueous plus COOH negative aqueous. So it's going to look like this, okay? So I guess I just did this whole problem for you. Well, either way, I mean, I want you to know it, so it doesn't really matter. So this is the first part. It'd be HCOOH. And usually it's a solid, but then it breaks apart. It makes these two things in solution.
Dr. Dillick.
Yes.
Yeah, how do you know to break the thing apart at the H, the hydrogen? Because it's like, when did you designate when to separate it?
Well, remember when we were back in naming? I know it's been like a billion years, right? And when we did the whole name, how long has it been since we named? I don't know, months. Okay, I'm gonna open up another page so we can look at the reason why I cut it there. Because I don't want to leave where I'm at. So if we did the naming thing, where's the naming flow chart? Oh, this is chapter 3. Actually, got to go all the way back to chapter 2. Wrong spot. Okay, cool. Naming flowchart. Yes. Okay. So what we named, our designation, it's all about what's in the front and what's in the back, right? So if the front was, let's say, positive ion, and the second was a negative anion, we end up, it was ionic, right? When we have an H in the front of any compound, we automatically call it an acid. That's the point at which it breaks apart. All acids that we know of, especially when we're naming, all have an H in the front. That's what's going to break off, okay? The only weird ones, okay, let's just be honest, right? So if you have hydrochloric acid, HCl, that's easy. We just say, okay, well, that's going to break off. This is the positive, and this is the negative end, right? So this would be negative, and this would be positive. The ones that are weird, and this is called monoprotic acid. It means I have one proton that breaks off. It's the diprotic ones, diprotic. That's where it gets a little strange, because we look at something like H2SO4, one of those will break off. So it'll be H plus HSO4 negative. It does this, and then it does another round where this thing will come off, but we don't want to talk about that because it gets really confusing. So if you take something like, I don't know, boric acid, H3BO3. Well, it makes a couple of jumps. Like first one comes off like this, and then you have H2BO3, and that'd be -1. And it's going to do it again and again. So the weird thing about it is we always look at that first H as where it's going to break off. And it's designated when you write out the chemical formula. If you write out an acid, we know the front one, an H, that's got to always come off. Does that make more sense, I guess, when you're looking at it? The rest of them kind of like just going back to the naming part of this thing. All right. So let's take a look here. Oh, I'm going to go back to this. Let's see if we can figure this out together. I want to give the answer away, but I think it's actually a thinking question too. All right, so I'm going to make a table, right? And then you guys can kind of look at what's going on. So I'm going to write down, here's acetone, right? And this is electrolyte. And it says acetone is non. So I'm going to put boom, right? Hypochlorous acid, right? So I'm going to say HClO is a weak electrolyte. So I'm going to say, I'll give it like 1 star. And then you have ammonia chloride, NH4Cl, right? NH4Cl, which is Salamaki, right? This is a really strong one. So guess what? I'm going to put it 1, 2, 3, 4 stars, okay? Now I'm going to answer the questions in a very simple manner, right? If you have 0.1 mole of each compound, so I'm going to start with this one, 0.10 moles, right? 0.10 moles. And this one, 0.10 moles, right? What are the soluble particles present in each aqueous solution of each compound? Will this guy break apart at all? Ava, if it's non-electrolytic. Acetone. So if I drew this out, CH3, COCH3. So the weird way this looks, if you guys want to see what it looks like, it goes like this. And this has 4 hydrogens near it. I'm sorry, 6 hydrogens total. And 1 double bond O. This is what this thing looks like. And it's non-electrolytic, which means it does what in solution? Nothing. Acetone is your nail polish remover stuff. Okay? This one right here will take nail polish off, but it does not dissolve in water. It's not polar. It doesn't do anything, right? So if you have 1 molar of this, what will you have in the end? The same thing, 0.10 molar. The reason why is it's not falling apart. It does not fall apart. Does it fall apart? You can think of it this way. Fall apart? No, right? How about this one? This one, it's going to somewhat fall apart. So in the end, you got to think about it. I'm going to have this, and I drew this guy out. I say HClO. It's going to fall apart a little bit because it's weak. So you're going to have some H plus ClO minus in solution. If I start with 0.100 moles of this, some of it, if it all fell apart, you'd have 2 moles, but you don't, right? You have less than 2 moles. So we got to think about it. You will end up with more than this. So I'm going to say it's going to be, how would you say, greater than 0.100 moles. But it doesn't all fall apart. Because if it all fell apart, it would be, I'm going to say, if all fell apart, it would be 0.200 moles. And that, what friends, would be a strong electrolyte. In this case, it'd be ammonia chloride. So this guy right here will be 0.200 moles. This is all, and this would be some. So you don't really have to answer this the way we just did it. I just did it in this little table, and that would be fine for answering that question when you submit it, okay? So if I was to draw this, and here's a chemical equation, guess what? I go CH, CH3, CO, CH3. I put it in solution. What do I get? The same thing. C3, CO, CH3. So there's actually no change. No change. This other one is this equation. This is just some change. The last one, if we think about NH4, Cl, in the end, you're going to have it all switch. And Cl minus. So you're going to double your ions in solution. You double your stuff in there. Does that make sense? Ish, maybe. I don't know.
In the chemical equation, how is the like NH4Cl different from the HClO? Like, how are they different? Because they both do the same thing. Like, they both split apart into 2 separate pieces.
The only thing that makes it different is this right here. This means it goes back and forth. This means it all falls apart. Does that make sense?
Yeah.
When you have this, that means it goes to equilibrium. That means like maybe only 5% of this. That means that, let's say if I had this many, this means I would have 0.095 moles of this. And guess what? This guy's going to break apart. So how many moles would I have on this side, guys? 0.005 and 0.005. So ultimately, I would end up with what? 0.1? No, 105. There you go. Moles. Why was that hard to do? It's just math. So I actually would increase the amount of ions on the other side. This may be a little confusing at first, and I think it's because the way I'm writing it all out here. But when you do enough of these things, it just it's going to click. So if I have this plus this, if I add them all together, you would have 1.005. If I think of it like this, because these are all in the same bucket. These are all in the same little thing. So I got to think I have some like this, I'll have some like this, and then some like this, all in the same container. So I have to add all these together. So I have 0.105 moles of stuff all in here now, because some of it fell apart. It's a little weird. It'll make more sense. I swear. I would not let you down. It'll all click. Everybody got this? I'm going to go ahead and go to the next thing. We're going to take a look at it as we're going.
Dr. Do it.
Yeah.
Will we go over this again, like in class?
Oh, we'll have fun with this. We'll talk about it a lot. Why, you don't like talking about it at home? It's just not the same, is it?
No, it's confusing.
I know.
Yeah.
I know. We're going to spend some time on this. This takes a little time. And I tell you what, the next thing I think starts to illustrate it a whole lot better. I'll be honest with you. This at first is it's sort of esoteric because you have to understand like a little bit of the concept. Once you start applying it, it becomes, I think, a lot easier to digest for law. So let's take a look here. I'm going to actually just sit in this thing. All right. So, and yeah, I'm going to put this here. And let's see. Let's do this. This is C-note formation. You might know what a C-note is. It's really kind of cool. So you could have, and I will illustrate this, and it's one of the questions on this one, 401. It says, explain C-note formation using carbon dioxide and calcium carbonate. Okay. I'm going to have to get to a blank sheet for this because this requires some fancy dancy illustrations. I get my page. All right, cool. All right. So let's do this. We have, for our viewing pleasure, this is the ground. Okay. And let's say we have here just normal water. Okay. Carbon dioxide, and that's the whole global warming thing. It can sit around in the air, but it does something really magical. It makes eventually carbonic acid, which is something to be fared about. It's C2H CO3, right? Carbonic acid, when it mixes with water, it does this thing, H2O. It just naturally occurs. You can see you have, what, 3 oxygens, 2 hydrogens, and carbon. So if you have an abundance of carbon dioxide, it actually goes into something called equilibrium. So I'm going to write the chemical equation. So H2O plus CO2 yields, in equilibrium, right, H2CO3. Now, you know how you know this occurs? If you drink a soda, you're drinking carbonic acid, right? So if you have a thing of soda, and you can just take a look at it, and you could just be mesmerized by this thing. This is a bottle of wine more than soda. I don't know any soda bottle that looks like this, but let's just go with it. You go home and just say you have Sprite because it's the right choice. I'm just picking Sprite because it's clear. And you take it home and you don't see anything going on here. You see nothing. But once you pop that lid, right, all of a sudden you see bubbles escaping, coming out of this thing. And if you shake it up and you throw some Mentos in, you have a party. But right now, you're like, where did these bubbles come from? And you say, oh, it's carbon dioxide. Well, carbon dioxide, it just can't sit in here like this. It actually has to merge with water and it forms carbonic acid. Okay? Now, you might be saying, wow, that's really interesting, but how does that form C-notes, right? What happens is if you have a lot of carbon dioxide build up in the atmosphere, and it's not normal. I mean, the number one greenhouse gas is just water vapor, right? 79% of it's that, right? But if you build up too much of something, you end up with a lot of carbonic acid. Carbonic acid is going to come in, and what it does, it's not so much the effect of this as much as it interacts with something. It interacts with limestone. So limestone is the same thing that makes up your bones, right? Same thing that makes up eggshells. It's calcium carbonate. Okay? So this is kind of a weird scenario, right? So if we have H2CO3 plus calcium carbonate, CaCO3, right? The end product of this is going to basically be the liberation of water again, right? Carbon dioxide is going to come back out, but it also knocks these guys out of their bonding. This would be +2 and CO3. This is going to turn around and interact with more water, right? And this is going to form carbon dioxide, right? Or H2CO3. It goes on and on. It's almost like it's a self-feedback loop. It just keeps going on and on. So what happens is these limestone deposits will eventually get eaten away, right? And then you get something called a sinkhole. It's fascinating when you think about it. A sinkhole, right? And sometimes it's like the macabre, that this is like the weirdest thing in the world, is that this water just keeps eating away at the limestone, and for too long there's a hole in the earth, right? And I think I talk about this, and it bothers me so much, because you're like, why? One was about the Florida guy that got eaten alive by laying in his bed, just got sucked up by the mouth of God and pulled into like the ground. It's just like, dude, that's rough, right? The other one is obviously involved with cenote formation. This is a great, right? And you can like look at videos of these things. You can spend a little too much time on this because it's fascinating. So it's in the Yucatan. Okay, I don't want to watch all this. How are cenotes formed? Oh, okay, here's a nice. How long is this? Oh, that's cool. I don't know if it's 1 minute and 35. No thanks. I don't want to see. Can you hear this? It's not saying anything, so maybe we can hear it. Oh, it's all visual. Nice. Oh, so okay, good. Nice. That was awesome. There was no talking. It was just all just kind of like spitting it at you kind of thing, which I thought was it's kind of a fun way of, I don't know, kind of looking at it, right? I just think it's fascinating that this is something that occurs. There's something else I was going to show that was really kind of cool. Oh, yeah. How about this? This pretty much covers this guy. All right. One thing I do want to talk about that I should probably show you before we run out of time, and you can look up, these things will be in the chapter. I'm going to go through the lead-2 nitrate reacting with potassium iodide. I'm going to do number 8 with you, okay? So we're going to do this together. I'm going to do the molecular, complete ionic, and net ionic equation for you, okay? And there, I should help with this concept. Remember all the crap I put on you as far as like learning naming, right? So I should say lead-2 nitrate. I automatically know it's going to be Pb, right? NO3 2 plus potassium iodide, which is Ki yields. And I'm going to go down to Pb plus KNO3. The next part of this whole thing I have to do is balance this chemical equation. So I got to put a 2 in front of this guy, and clearly I put a 2 in front of this. So this is my molecular equation, right? I also have to do a new thing, which we have never done, but we're doing now, is we have to put designations. These things are in solution. So I got to put aqueous here. I put aqueous here. I put aqueous here. And I put aqueous here. These are, well, actually, no, this is not going to be aqueous. Oops, messed up. This is actually going to form a solid. So I'm going to put a solid here, okay? So these things in solution, if I had a, how would you say, an Erlenmeyer flask or something like that, I can have PbNO3 2 would be in solution. This falls out of solution. It's called a precipitant. So this is going to be our precipitant. Like I said, when you read through the chapter, it should help make more sense. The complete ionic equation is I break apart all the things that are aqueous. So let me do this one, and you'll see how this works. I go, this would be Pb plus 2 aqueous plus 2 NO3 minus aqueous. Now this is strange. That 2 is going to come up in front of the NO3. Remember, they're not going to be attached together anymore once they fall apart. Then this guy would be 2K plus aqueous plus 2I minus aqueous yields. And this is a solid. I also like to think of the S as being sticky. It sticks together. So it's going to be PbI2. It does not change. That's what that would look like. These guys fall apart. 2K plus, that'll be aqueous, plus 2NO3 minus aqueous. For the net ionic equation, you basically are going to go through and cross out all the things that are the same on both sides of the equation. So lead's here, but lead's now joined with something. I can't cross them out. So that says 2NO3. This is 2NO3. I cross him out. He's got a special name. He is called a Spectator Ion. Basically, you could switch him out for anything if they end up being the same size. They're really not part of the chemical reaction. So we have K plus here, we have K plus here. I can cross him out. He is also a spectator ion. So my true chemical reaction, when you really think about it, and I'm going to put it down here because I'm running out of space, it's Pb plus 2 aqueous plus 2I minus aqueous yields PbI2 as a solid. And this is my net equation. This is the complete ionic. It's a solid, and therefore it does not break apart in solution. It sticks together. The only time you do the aqueous thing is when it comes apart in solution, they're separated. He won't separate. It's a solid. We'll do several of these, and obviously, the practice that you'll get for doing this part right here will help illustrate this point a little more, honestly. Let's move this back over here. So just to kind of let you know, on Friday, obviously, we're going to go through the answers to these things. So your grade's going to be more or less a completion grade. You're going to make an attempt on it, try your best. This thing over here, like writing the actual, how would you say, the definitional stuff, I kind of expect you to be able to do that. But these problems down here, you just want to practice them. I mean, to try to do them. But we're going to go through them. And therefore, you're going to check your answers to see whether or not you got it right or not. Okay? I'm not taking off if you got it wrong because you're just learning it right now. Does that make sense? Everybody kind of got that? I'm going to try one of these down here. This one, you can see how I did that one with the calcium chloride and sodium carbonate. Okay. And somebody should be asking me a question right now. There should be a question like, it says, what is the solubility and what's the cutoff? You could do one of two things. Look it up in the book, or I'm going to show you my handy dandy rules for doing things. So I'm going to go back here. I am going to erase this, and I'm going to do my soluble and insoluble chart. This chart right here is kind of a very, very simple way of looking at what's going to be in solution and what's not. So all these things are soluble, except that what you see in red. So let's look at our last example, okay? So I had PbNO3 2 plus KCl yields PbI2 plus KNO3. And this was our first chemical reaction. We just kind of did this thing, and we called this our molecular equation. And now I got to figure out whether or not this is soluble or not. If it's soluble, I put AQ next to it. So here's NO3. Anybody who hooks up with NO3 is soluble. So I can put aqueous next to him. He's automatically soluble. How about this guy? Well, he's KCl is soluble except if he hangs out with these guys, right? And it says if any cation is 1A or NH4, it's always soluble. So if we think of our periodic table, which, you know, we sometimes have to reflect back on, if I go here and if I go here, where's my index page? Anybody in this table right here, they are always, is that how you spell always? No. Always soluble. So if it's lithium, such as lithium nitrate, right? NO3, sodium nitrate, potassium nitrate, rubidium nitrate, cesium nitrate, francium nitrate, or anything these guys associate with, they're automatically soluble. They're always going to fall apart in solution, right? So that's just something that you'll see when you do these chemical equations. They try to keep it like this. These are your players, and then the other guys that we see is it's mercury, lead, and silver. These guys right here, these guys always seem to fall out of solution. These always tend to be insoluble when they're hanging out with stuff. And that's the reason why I kind of made that little table, is these guys show up in all the chemical equations. These are the ones that seem to show up the most, okay? So a good example is if I have silver nitrate. Well, nitrates are always soluble, so this is always aqueous. And then if I add it to sodium chloride, and this is actually a thing we did in the lab, AgCl, well, he's going to fall out of solution because he's barely ever soluble. But the reason why he is soluble is because he's hanging out with nitrate. We'll get more into this. I mean, and obviously it's just something we just got to kind of goof with till we get it. So let's take this and let's erase parts of this.
Dr. Dewick?
Yeah.
Grace got kicked out of the meeting and can't join back in.
What?
She said her internet.
Is it because I'm not letting her in, or she just can't get in? Oh,
She
well,
just can't.
it's her interwebs. Okay, well, I'm recording this. She can go back and take a look at this if she wants. I can clip it up, make it look nicer. And then let's go back to this shindig here, right? So look what happens. This becomes, because of the way this is set up, this will become a solid. Ooh, wait, I need my marker pen. This becomes a solid. This becomes aqueous. And this is going to be aqueous. So we know that this is the guy that falls apart right here, but then he gets stuck and he cannot come back together. He cannot fall apart after that. So when you're doing the homework, you could just use this sheet, which would make it a whole lot easier. Let's take another look at the ones on the sheet, and then I'll show you how it works, okay? So let's go to, is this it? No, I don't want that. This is 402. So, using the soluble guide, predict whether each of the following compounds is insoluble or soluble in water. Okay? So, this one's magnesium bromide, MgBr2. Okay? I look at this thing, Br are soluble, except with those guys, it's magnesium. Definitely, he would be soluble. It's that easy. Okay? So I would sit there and look at that. And obviously, you don't even have to do that problem. I'm just doing ones as an example, right? How about this one, PbI2? Well, let's look at that. So we have Pb. I'm going to write down the thing. PbI2. This is my exception. He's in red. He's normally soluble, but he's not now. So this would be a solid, okay? Just kind of looking at what we have here. The next one says NH4CO3, all right? So I'm going to go here. If I look at this, I got to go down to this chart to find that compound. It's always the same ones, too. So I had NH4CO3. And, of course, if I was to balance this, I'd put a 2 in front of it like this. And it says it is insoluble except with 1A or NH4. He is NH4. He's definitely going to be soluble. We can put an aqueous next to him. As I said, the tables kind of really makes it sort of simple for doing these things, right?
Wait,
the next one
weird.
says, yeah.
I don't understand. Why is I2 solid, like on the chart? Is I2 just always solid?
No,
Like,
it's the lead. See how the quotation marks on it? These things, I kind of shortened it. This would be AG.
oh, it's all of them. Okay, I see.
Yeah, I'm sorry. That's my ditto marks. I don't know if they look good. So this, I didn't want to write it out 3 times because I think it makes the table even messier looking. So if you're one of these guys hanging out with them, you're not soluble, right? Does that make sense? Except these guys in red, which now I put them in black, which screws everything up. But if you had something like, let's say, silver bromide, AgBr, it's insoluble. It's a solid, okay? And let's say, how about this one? Calcium sulfate, CaSO4. It's going to make us solid because this is one of the groups in red here. So I'm sorry about mixing the colors. I kind of messed everything up, but kind of makes it goofy. So this table, obviously down here, is these are mostly soluble, except for their little exceptions. I'm going to clear this out for a second. And these guys down here, they're insoluble, except for the exception. It's always 1A and NH4. So lithium phosphate. How about this one? Is this soluble? Li3PO4. Is that soluble or insoluble? Emily Leon.
Insoluble.
He's 1A. Except he's the exception. So he would be soluble.
Okay.
Right? Ready? How about this one? Suppose I took this guy. Suppose I had this one. Na2SO3. Katie Galgano, is that soluble or insoluble?
Insoluble?
No, it's soluble. It's 1A. Okay, how about this one? OH. How about this guy? NaOH. Paige, soluble or insoluble?
Soluble?
It is soluble. I got one right. That's cool, right? How about this one? CaS, calcium sulfide. Soluble or insoluble? Luke Shokoff.
Soluble.
It is soluble. Everybody see how this table kind of works? The table, if you put it like this, they have a table in the book. It's just a little messier. So I try to make it like really, okay, these all 1A and NH4 interacts with all these. And then you have these guys helping along at this point. We're about maxed out on time. I went a little longer than I thought we were going to be, but you know, we were having fun. So homework. Let's talk about the work at the home. We pretty much knocked out. Where was I? Let's go take a look at what we did. I'll put a folder for collecting this stuff. 401's pretty much done. You guys did that with me, right? This is all done. So you're going to take that and yeah, put this up in the collection folder. I guess you can answer those last few ones. They're not too hard. And then this thing, it's a little bit of book reading or whatever to kind of go through these things. And then you're going to try these problems down here. You're just going to try them, and we'll talk about them on Friday and hopefully iron out the differences. Okay?
I
Everybody see
don't
what we got going
understand
on?
how CaS is soluble. Because
Yeah,
I
Which
love
one?
A.
yeah,
Which
because
one?
it's 2A. I don't know why it's soluble. Because it's
NA.
No,
Which one?
it was like CA, right? CAS.
CAS.
CAS?
Yeah.
Yeah, I don't understand how that's soluble.
Insoluble, except for now we have this. These guys are in there now. Those are red ones. So any of these, so if we think about it, anything 1A, so it's 1A plus S. So it'd be 1A, 2S, or CAS, SRS, and BAS. These are all going to be soluble. They're all aqueous. These are exceptions. It's insoluble except for this group. Does that make sense? Essentially, these two tables are kind of flipped. It's really weird, but that's how they do it. I can show you another table, but I don't know if it'll help. I think it'll just make it a little more confusing. Does that make it more sensible or no? Believe me, everybody gets a little confused on this, so don't get upset and say, oh my God, I'm not getting this. And then you work with it a little while, it'll start making sense. So, for example, how about if I had something like this? Let's grab this guy. Calcium carbonate. It is a solid. It is insoluble. Otherwise, your bones would dissolve in water. You'd be in trouble, right? However, if I take this guy and I put NaCO3, Na2CO, this is sodium carbonate. This is aqueous. This is baking soda. This will dissolve in water. Okay? So 1As are the exception. Otherwise, they're normally insoluble. So lithium carbonate, LiCO3, sodium carbonate, NaCO3, potassium carbonate, CO3, and these are obviously 2s in here. These guys are all soluble. They are the exception, okay? Now, most of these guys down here are going to be insoluble. Like, say, if I had aluminum hydroxide, AlOH3, this is what Malox is. You ever seen Malox antacids? It's aluminum hydroxide. I don't know. Anyways, these guys right here are insoluble. In fact, it's white because it's in a suspension. It's really what it is, right? However, you could take some of these guys, like calcium hydroxide, CaOH2. That is soluble, so we put AQ. So this guy, anybody 1A, calcium, strontium, or barium, you have a barium hydroxide, BaOH2, he's going to be aqueous to some degree. And there's a cutoff. It's in the book. I think it's 0.01 molar. If you can be more than that in solution in 1 liter, then you are considered soluble, right? When you read the book, you'll see it. Is everybody good? I think this class ends now. That's why I have to get ready for AP Physics, which is going to be kind of crazy, but